welcome to the session. Greeting of the day. In previous classes, we are on the talk of discussions of the solidification processes. In solidification process, we have seen about the nucleation, and then there we have also discussed about the homogeneous and the heterogeneous process. Then here we have also discussed about the structures of equiaxed, then columnar, then also we have columnar dendrite. These are things that we have already discussed about those in the previous sessions. In continuous with that, we want to see about the solidifications of pure material, solidification of the alloy system. See, now we move much more clear here. There are three types of structures which is possible to move. What are those three structures? One is a columnar dendrite, equiaxed, and equiaxed non-dendrite. We need which one? We need this one. Equiaxed non-dendrite we need. Equiaxed if it's dendrite, what happens? No use. That is short corner again. You see, the columnar dendrite. So we have, this was the mold. See clearly, this is what the mold. At the first initial, this green color is belong to mold region. Okay? And then from the mold region, we are adding this here, the impurities are there. Right? It becomes solid. I am defining what is columnar dendrite. So it goes, the first one, it goes in perpendicular where it looks like a column. It is one like column. Right? This is what a columnar dendrite. Where is dendrite? The tree forms. That is called dendrite. The tree is nothing but a dendrite. Right? It is a columnar dendrite. What is equiaxed dendrite then? So see, the same dendrite formed in such a way by breakings. So that is called as equiaxed dendrite. This is also not needed. So this too is not recommended, because already here also the columnar sharp dendrites are there. Here also equiaxed but dendrites are there. These two are not recommended. But these are the chances are there. When is the chance? When we are not having, when the homogeneous process takes place, these are the chances. We are avoiding this too. We should add impurities in such a way heterogeneous process takes place. So that is what? Equiaxed non-dendrite region. This is what we need. Heterogeneous, started, cooled, nucleated, cooled. In such a way we need. It is nucleated, cooled. So this is what? The equiaxed non-dendrite region. Right. In general, we will go a little bit. A solidification of pure metal. This may be the question. Solidification of pure metal. What happens there? We have studied already these things in metallurgy. What happens? We see how a look. This side we have a temperature. This side we have a temperature. This side we have a time. Why? The temperature always takes time to reduce from high temperature to low temperature. When you are switching on the AC, it takes time to cool the room. Similarly, when high temperature 1500 to room temperature it should come, takes time. We understand this. So what happens? We have studied this. A pure metal converts from the liquid to the solid at a single temperature. So the single temperature is here. Right? It comes down slowly. A time increases from here to here, but there is no change. It is still in the liquid. At a single point, crystallization started and ended. It becomes a solid here. This is a solid cooling. But a solid cooling, it does not mean it is a room temperature. It from maybe 1500 for steel, it is a pure material. It may be 1400, 1300. In such a way, from there it comes to room temperature here. Right? So we understand from this figure that the pure metal cools at a single point. That clearly we understand. Crystallization and freezing of the pure material occurs at a constant temperature. This is what the constant temperature. This one, at a constant temperature takes place. However, undercooling is required for the beginning of initiate the phenomena. What happens here? They are talking about this point, a single point. They are talking. This point, when it comes fast from liquid to downwards, it takes a little bit a curve, but it is not mentioned there. But it practically it little bit goes down. They are telling it is a single point cooling, but it takes a peak value of a small temperature 1 or 2 degrees. It goes down and comes and maintains those temperature. Okay, and it cools down. About the pure metal. So here, the solidification. What I have told you like this. The wall, this is the wall. So this is the wall we have. So this is the wall. These cases are exposed to air. This side is exposed to air. What happens first? There are two nucleated points which started. Here it is started, here it is started. But here in the walls we have impurities. We have impurities here. We have impurities. This point is impurity, this point is impurity. This points, every point belongs to the impurity. This impurity makes the heterogeneous process and it cools down in immediate. So it is nucleated and started to go in this direction. It started to go in this direction, but what happens? It joins here and then it moves in other inside. The process, what I am telling here, it's nucleated here. It nucleated at the walls first. It nucleated the walls first. But it started to cool down in both directions first, not here. Because that is very hotter than this. The point, easiest point should catch. The easiest points near the walls where the air is there. Where the air. Therefore, it fills this first layer. This is layer 1. Then the second layer goes inside that we see. You see? This is the second layer which forms next to that. What happens there? As a solid skin of this formed, which then grows inside, which then grows perpendicular to the mold, which then grows perpendicular to the, which is the perpendicular? This one is the mold and this is the perpendicular. This one is the perpendicular. So it forms at the first layer and then goes perpendicular to the mold to fill, converted in from liquid to solid condition, from liquid to solid conditions. Right? In a stable manner, with a smooth, flat, or solid and liquid interfaces. This is called as planar. This is called as planar mode of solidification. What is the planar mode of solidification? First started from the wall, then it is started perpendicular to the mold direction. Then it is called as planar mode of solidification process. So factors altering the planar mode. What are the factors altering here? Why it should not happen? Actually, the heterogeneous process should nucleate here and it should move inside. That is what the concept. But what are the factors may differ these things? How it differs? You see, absorption of gases. If the absorption of gases is there, what happens there? Some nucleating circles may form. The evolution of gases, in the gap in the middle, there will be gases. These gases will interrupt, will disturb the solidification process. Therefore, that is one point of making this number 1. Number 2, reaction between the crucible and the materials. Where is the crucible? I mentioned you, this is the mold box. I mentioned you, this is the mold box. And then this may be the crucible also. Where is the crucible? We have to take, we are taking from the cupola furnace, we are tapping out and we are taking the crucible and coming down and putting into the box of which want to be cooled. So here, when it is taken from cupola furnace to the crucible, when a cupola furnace to crucible, here the reaction may take place due to already containing impurities. This makes the reaction. Number 1, gases may make the reaction. Number 2, impurities in the crucible or impurities in the walls may make the reaction, which stops the planar mode of interactions. Number 3, presence of impurities or alloys. That I told you, in the walls we have impurities here. This changes, but this is good for the formation of equiaxed grains. But these two are not good. Formation of gases and formation of crucible reactions, not good. Okay. You see, the formation of dendrite growth. Here, the term dendrite comes from the Greek word that we know, dendron, which means a tree. This is what from the beginning itself I am telling you, a formation of tree. Almost all freshly crystallized alloys are composed mainly of thousands or even millions of dendrite crystals. This is taken from the microscopic level. Actually, while doing solidification process, this dendrite forms in this way. How? See the tree. This is not a Christmas tree. It is a dendrite formation on the casting process. It forms from the starting point, from the walls, and its columnar grains are developed here. Columnar grains are developed there, and from the columnar grains, it is developed at the side levels. It's like a tree. It's like a tree, which is called as dendrite structure, which is very sharp, which is not good. It is a key. It's a key point for crack. It's a key point for the crack. Therefore, it is not recommended structure that we should keep remember. It is taken at a high SEM images of microscopic level and high magnification for the visibility. So, first stage of dendrite growth, how it forms. We are understanding the solidification process, how it happens. This side we have solid, this side we have solids, and therefore other end from this is the wall. Other side we have liquids, and growth takes place like a tree, like a column first. It takes place as a one by one. It develops there. It is a dendritic arm. So see, after creation of this column, we have seen this column in the previous image. So this is the column developed. From the column, it develops the tree again. So that is what I have mentioned in the next one. Secondary arms. First arm generated a columnar. Then from the first arm, second arm it is generated up and down. First arm, second arm. Likewise, it is multiplying. It became a Christmas tree at last. So find this will be such an image. We have seen the original SEM image also. Animated or a picture. I want to represent how this dendrite formation will takes place. So this is the original image which is taken at 80 microns level in the cell. So such a way we can able to see the original image how this dendritic structure are formed here. See, a tree. Many trees are there. It is unhealthy for the casting process. The cooling curves of an alloy system you should see. We have already seen the pure material of a pure material. Of a pure material, such that we have a cooling from the high temperature at one single point cooling freezing temperature, and like this we have seen. Here it is a liquid solidification starting. Solidification start, solidification end. This is what we have seen for pure material. But what happened? For this alloy systems? You see, this also we have already seen in the metallurgy. But for our introduction part, for the casting process, we are mixing n number of alloys to make a product. From there, we want to know these things. For a few, I have taken here, for example, a copper-nickel phase diagram. A phase diagram for copper-nickel alloy system has been taken for the example of solidification of the alloy system. The casting process can be happened in the alloy of copper-nickel. Yes, therefore, cooling curve for a 50% of nickel, cooling curve of 50% of nickel and 50% of copper resistance during the casting process has been shown here. Okay. In the x-axis, we have taken nickel to copper. It means nickel is started 0 here, nickel is 0 here, and the same nickel is 100 here. The copper is 0 here, the same copper is 100 there. So it is reversed. So here it is copper 100% is melting point. We have around 1455. The copper's pure material cools at a single point, 1455. Similarly, the nickel 100% cools at a single point of 1083 degrees centigrade. In the middle, what happens? In the above curve, we can tell in the above curve, this is the region of liquidous line. And similarly, we have one more line of solidus line. Here we have a solidus line. In between we will have liquid plus solid constants to make the view of these cases. So here I want to compare this. I want to compare the solidification process that takes place from the liquid to the solid zones, and the time taking of between these two I have taken as a graph between these three. It means the starting point of the liquid takes place at here, and the end point of this liquid to solid transaction takes place in between the gap transaction of time. Where is the time taking? The time taking process takes place from here to here. But it does not mean it completely transferred from the liquid to solid from this region to this region. The region of starting point begins here and it ends at the last point. It does not mean it belongs to the ambient temperature. The ambient temperature have to go from 1300 to the room temperature here. Therefore, this time-taking process where the casting has to be fallen from the high temperature to low temperature with respect to the interaction between the air surfaces from the wall zones. We can able to take an example of having a box where we want to make a cooling of the cast material. I have taken a liquid zone. In this process, initially I am considering the outer part of the material, outer part of the box, where the solidification started at the walls first. Because as it is interacting with the air components at the outside surfaces, it cools first. And from later, from the wall, the solidification started from the second layer. It started to the second layer. In the second layer, it started to go from the second. You see, likewise it moves. One by one, slowly, the interaction process takes place and completely, finally, it becomes the solid process. See, from here now, we have understand the concepts of making the alloy system or taking time-taking process with respect to temperature in the y direction and the time in the x direction. So I have compared the component of copper and nickels. So see, I want to tell you how much this time-taking process takes place. A solidification of patterns for grey cast iron I have taken here. The solidification process of grey cast iron I have taken, and in 180 seconds of square casting process, 180 of square casting process, these cases there we have considered, and after 11 minutes of time, what happens there? After 11 minutes of time only, at the center point has been reached there. At 11 minutes of time afterwards only, the center point we have reached here. Until then what happens? There is no change in causing of the center point here. The starting from the walls takes place, starting of the wall takes place. Afterwards, from the walls, it goes in developing from here. It develops. One by one it develops. One by one it develops there, and it takes more time to reach. But at the time of 11 minutes, these dendrites are columnar joined together. Then even though the solidification process does not completed, it's completed at 1 or 2 minutes. It completed entirely at 1 or 2 minutes. It takes time from 8, 11, 40. This is the situation of development inside of a square. I have taken a 180 mm square. There, these are the various walls regions. This is the left side wall, this is the right side wall, top wall, and the bottom wall. So in this all over the exposed, as it is all things are exposed to air, all regions started to solidify first. All regions are started to solidify first. Later, from the 8 minutes to 11 minutes, the solidification inside increases. From 11 to 40, again the solidification process increases. Accordingly, the various types 60, 90, 1 or 2 minutes, the solidification process keep on increasing. And finally, we are reaching at the center point where this solidification process completed. So likewise. I want to play a video here for our better understanding.
Explain the solidification of metals and alloys. First, let's discuss the solidification of metals. When we pour the molten metal in the mold cavity, we see that the solidification process starts from the sides of the mold, then moves towards the molten metal. This is because the sides of the mold provide sufficient cooling to the molten metal. After some time, we see that the molten metal solidifies in the form of randomly oriented crystals. The region where the crystals are formed acts as the production area and is called the nucleus. When the molten metal solidifies further, we see that the shape of the crystals changes to a long columnar crystals. Having their axis perpendicular to the sides of the mold. Thus, the shape of the molten metal crystals formed will be as shown. Note that during solidification of metals, the temperature remains constant. This can be represented graphically as Now let's discuss the solidification of alloys. When we pour the molten alloy in the mold, we see that the solidification process takes place in the same manner as in case of solidification of metals. The only difference is that the crystals formed will have a dendritic structure as shown. Note that during solidification of alloys, the transition from liquid to solid state occurs during the change in temperature. This can be represented graphically as Thus, we can say that solidification of metal results in the formation of long columnar crystals and solidification of alloy results in the formation of crystals having a dendritic structure. The related terms are
From the video, we have understand those process of how the solidification takes place. Right. You see, some problems are there to understand what happens in these solidification treatments. I'm counting these three. These three are the important points to be considered for solidification. They are the shrinkage defects, hot tearing, and evaluation of gases. You keep on remember those words. Shrink, you know these words already. Shrinkage refers the molten metal got shrinking at a point. That is a defect. Hot tearing, the crack happens at a hot condition. That is one defect. And then the evaluation of gases, the entrapment of gas involvement in between the mold cavities. These are the various defects that we are going to see now. Right? One by one we will go. So the summary. In this class, we have talked about the solidification process. In this, we have talked about the heterogeneous solidification, and then also we have talked about the homogeneous solidification, and we have seen the structures of equiaxed, columnar, and then dendrite. The remaining part of the subjects we will see in the next class. Thank you.